for responses back, etc. So with that, I give it to Chris.
All right. Can you guys hear me okay in the back? Is that good? All right. Cool. So I have a lot of slides, so I'm not sure I'm going to make it through all of them. So definitely ask questions throughout, but if you don't get your question answered, come find me afterwards, please. All right. So hopefully you guys saw my talk yesterday, but if not, I'll do the 30-second version. Why did we go down this path of pursuing NVMe? Why did we want to build a JBOD around it? So first of all, we wanted to build a scalable solution, a solution that allows us to scale IOPS per terabyte as the capacity of devices continues to grow. And we also want to be able to make sure that we can properly align compute and storage resources on a per application basis. Right, so we don't want to be in a situation where we're stranding compute resources or storage resources, because ultimately it's not a very cost-efficient solution for us. NVMe is also open source, and in keeping with that trend, we're going to be submitting all of the design files to OCP. That will include the BMC code, which is going to be based on OpenBMC, and as well as any software utilities that we need to implement to provide monitoring or management infrastructure. And then finally, the design is built to support multiple form factors. I believe this is important because the SSD, especially, or I should say maybe the non-volatile memory product market is still very much evolving, right? So the next few years, we'll see an introduction of all kinds of interesting new storage devices, maybe on different types of media. And to accommodate that, we want to make sure we can support different form factors that might be more optimal for one type of media or one type of application over the other. So the design is going to support 3.5-inch, 2.5-inch, and M.2 devices. All right, so from a design objective perspective, we wanted to build something that was modular, had the ability to implement flexible configuration, and then also be compatible with upcoming PCI SIG standards. We don't want to differentiate if we don't have to, so we want to try and be aligned with that as much as possible, even if the standard is not quite ready yet. All right, so let's get into the details then. All right, so Lightning overview. Basically, the way Lightning works, on the left side, those gray boxes show the compute servers. Compute servers, in our case, are the Leopard Broadwell servers, for example, the dual socket Xeons. But realistically, it could be any server that you want. The server itself will have a card installed in it that we call a retimer card. This is just a standard low-profile PCIe card. All that is on this card, and I'll touch a little bit more detail in a minute, is basically a retimer. All that does is redrive the signals across the cables so that we can make it across longer external cables. The PCIe then gets connected into what we're calling the PCIe expansion board. This board is what sits at the front of the system. And the switching component, the BMC, and some of the other support circuitry are going to be on that board. So the vast majority of the active componentry is at the front on a separate modular piece that you can replace, upgrade, repair as needed. So we basically have up to 32 lanes of PCIe coming into the system. Those get connected into a switch or multiple switches, as the case might be, and up to 30 lanes of PCIe going downstream to the SSDs. The BMC is also connected into the switch with a by one PCIe link as well, and I'll explain that further in a minute. So if you look at how the data actually flows, it'll go from CPU through the retimer, across the cables, through the switch. The switch will then map it to the appropriate endpoint and forward it down to the SSD. All right, so retimer card. So what's on the retimer? It's really simple. We intentionally did that to keep the cost down and make it a little bit easier and lower power, so we don't have to add extra switching here as well. So basically, it consists of a PCIe retimer chip. We specifically picked the retimers for two reasons. One, we wanted to make sure that we could truly drive it over at least 2 meters worth of cable. There's actually margin, so we may actually be able to push it farther than that. But for us, for now, we're testing at least up to 2 meters. The other benefit of the retimer is we wanted the retimer card itself to be configurable. So there may be cases, for example, if you don't need a by 16 connection to your storage, maybe you only need by 8, or maybe you only need by 4, for example. In which case you could have one retimer potentially connecting to multiple storage trays. So the pinout of each of the by 4 connectors here is exactly the same. So that way you could fan this out to up to 4 storage trays, basically. So the retimer will support that because it can handle bifurcation as well. So you can bifurcate it up to 4 by 4s or 2 by 8s or 1 by 16. There's a USB hub on there. So the purpose of the USB hub is basically it will provide a USB connection from the PCH on the dual socket server. And that will go all the way over the cable to the BMC in the Lightning system. Purpose of this is it provides us an out-of-band management mechanism to the BMC itself. We did not want to have a network connection going into the Lightning system, as that doesn't really work well in our infrastructure. So we'd prefer to route all of the management traffic through the head node itself. So this is the path. This is a path to get to that to the BMC. There's also let's see. Okay, so the clock buffer. So basically, this just fans out the incoming reference clock from the edge connector to each of the 4 mini SAS connectors. And there's also an I2C MUX, which basically does the same thing. Again, you could potentially use this for management traffic between the BMC on the server and the BMC in Lightning. The problem is because it's I2C and most BMCs are actually relatively slow, for this path, it's not really an ideal choice, right? It's too slow to do firmware updates, for example. If you're doing a lot of sensor data collection, there's no way that's going to provide you enough bandwidth. On the other hand, the USB connection provides more than enough bandwidth to do that. All right, so the board at the front, as I mentioned, is called the PEB or PCIe expansion board. This basically replaces the SAS expander boards that we had in our previous systems that are SAS-based. So this consists basically of a PCIe switch or switches. This will fan out the uplink connections that come into the system down to the downstream devices. As with most PCIe switches, they're extremely configurable. So basically, just by loading a different configuration file, which is typically stored in a SPI E2 PROM, for example, you can map different host connections to different endpoints. So that basically allows you the ability to soft partition or virtually partition that switch into separate pieces so that each host has its own allocation of physically assigned drives. Now, obviously, if you want to go further, you could certainly do that. You could implement non-transparent bridging and implement some form of HA as well if you want to do multiple host support. But for now, we're at least for us, we're primarily focused on just providing the ability to partition that switch into multiple volumes. All right, so I mentioned there's a BMC on here. So we're using the same BMC, the uprated version of the same BMC that we use in our compute platforms as well as in our switches. So it's also an A-speed part. So the circuitry that we're using here is very, very similar to the circuitry that we used in Honey Badger. We had to make a couple of changes because obviously the design is a little bit different, but that basically allows us to port code over very quickly and very easily. So we don't have to start from scratch every time. I'll have a little bit more detail on the BMC in just a minute. This is the AST2400 part. The reason we picked that is not because we actually need VGA support, but because we wanted to have the PCIe connection there. Because that way we have yet another path to get to the BMC, and this provides us an in-band option for the BMC. And then at the front, we have 2 sets of mini SAS HD external connectors. Each of those quads is 16 PCIe Gen 3 lanes. And the cables that we're using are a modified version of the mini SFF 8644 cables. The biggest difference between them is really that we have added some additional sideband, and I'll cover that in just a minute. But otherwise, the cables are the same. So that was important to us because we wanted to use a high volume, standardized and robust cabling solution. And this is also the direction that PCI SIG is going. So in the future, this will be likely to be the standardized solution for PCIe external cabling. All right, so this is a little bit of an eye chart for people sitting out there, but basically this shows the pinout of the cables that I was just talking about. So the cables that we're starting with, actually, you can do either by 4 or by 8 cables. So we're going to start with by 8 just simply because it reduces the number of cables you have to plug into the systems. As I mentioned, the cabling is pin compatible with the upcoming PCI SIG spec. So while we have additional custom sideband in here, it doesn't preclude you from using the standard cables when they actually become ready. All right, so let's talk about the sideband. So as I mentioned earlier, we have USB going across the cables. So we have a couple of pins defined for that differential pair. And we also have the I2C or a bus connection going all the way across the wire. Typically, the SAS cables don't actually route that across. They just route it to the PCB and the connectors. You can identify the type of cable that's there. But we chose to route it across as an additional sideband path. And then we have the PCIe sideband. So we have PCIe reset, and we have PCIe clocks. The reason for this is for at least for now, until the ecosystem matures a little bit more in terms of independent reference clocks and working out some of the kinks there. This allows us basically to do a common clock architecture through the entire stack. All right, so here's a couple of the PCIe switch configurations. So as I mentioned, you can basically support different types of topologies simply by modifying the configuration of the PCIe switch. So there's no hardware, no BOM changes. There's not even really any software changes. You're just reloading the config file into the switch itself. So on the left, we have a kind of 2.5-inch U.2 type of configuration. So each tray has 15 2.5-inch U.2 drives on it. The connections, each one of them is a by 4 Gen 3 connection. On the right, we have an alternative option, which is to do basically 30 by 2 Gen 3 connections. So we simply take the U.2 connector that is on the drive plane board, and we bifurcate it in the switch. So there's no additional circuitry required there. There's an adapter board that I'll show in just a minute that will allow you to plug in 2 M.2 drives per drive bay. But there's no additional switching or anything needed. So we can get complete end-to-end by 2 connections without having to do anything in addition. All right, so PCIe sideband. As I mentioned, the drive plane has a U.2 connector or SFF 8639. So we're using the standard connector. In terms of the sideband that we have connected, obviously we have PCIe clocks going there, so we can also support common clock end-to-end. But there's a couple of other signals that you really need to be able to fully support hot swap, in the fullest sense. So there's a presence connection. There's the ability to control a local attention LED. So that way you can light that LED and tell a technician this is the slot that needs to be serviced. We added the ability to actually have slot level power control. So there's a FET on the board per slot that you can then control through the sideband. And then finally, PCIe reset. So there's a couple of key points here. The first one is that all of this is either directly connected to the switch or through an I/O expander that connects to the switch. And all of that circuitry is on the switchboard. So that's important for 2 reasons. One, that basically allows us to do all of this control in band over PCIe. So you don't have to do any form of other out of band control for the BMC or some other mechanism. So we can basically write a common utility that works over PCIe without us having to, write something custom on the side. So basically, whatever we create should work for anybody if they wire these up. The second thing is because not all switches are created equal, and there's some variance there in terms of the implementation choices that each vendor makes. All of that circuitry should stay on the switchboard with the switchboard, right? So we drew the line in the sand there, so that way the drive plane board is completely agnostic, and you can plug in whichever switchboard that you want, or maybe a future generation of a switchboard, and you don't have to redesign multiple boards as a side effect of that. All right, so BMC, I mentioned earlier that it's based on OpenBMC. So Jubin's around here somewhere, and he can probably talk to you in a little bit more detail about some of the functionality that we're putting in there. But this is already a work in progress. And of course, it's based on OpenBMC, so everything we build there is going to go straight back into GitHub. This kind of shows a high-level I2C/SM bus layout. As I mentioned on the left, we have incoming external connections with I2C going across the connectors. So you can either talk to the server BMC if you chose, or multiple server BMCs potentially. Or you can read information from the cables as well if they implement an E2 from there. Then we have a set of local sensors on the PCIe expansion board. So this is temperature, your Peru ID prom, voltage monitors, clock generators, and a hot swap controller. So the PEB itself is hot swappable, so we have a hot swap controller there. That's also nice because we can also read the temperature and temperature, yes, but also power consumption from it. So we can read power consumption at the chassis level, and we can also read it at the switchboard level. So we can kind of separate the two if we're interested in that data. We also have a connection into the PCIe switch itself that basically allows the BMC to potentially do firmware configuration updates out of band if we so chose. It also allows it to monitor the switch for errors, collect error log information, and ultimately push that back to the host and report it up the chain. And then we have some sensors local to the drive plane board. So we have a Peru ID, more temperature sensors, some voltage monitors. And then we have some connections going to the local clock buffers on the drive plane board. And then as well as the U.2 connectors, there's an SM bus connection there also, one per slot. And the benefit there is that ultimately the BMC will be able to read temperature information out of band over SM bus, and it can incorporate that directly into its fan control algorithms. So we don't have that option today with hard drives. So this is going to be really nice to be able to have a fan control algorithm that we can implement that will actually use running drive temperatures versus having to guess at what those temperatures might be under different conditions. And then finally, same as Knox or OpenVault, we have the same set of sensors, hot swap controller, and so forth on the fan control board and back of the system. So that part of things has not changed at all. So the USB comes onto the PCIe expansion board and goes through a hub and connects to the BMC itself. We also have another sideband path here to a USB to SPI converter chip. The benefit there is if anything ever happens to the BMC, it locks up, it needs to be reset, it needs a firmware update because we can't do it in band anymore. We have a sideband path here to basically either reset the BMC, reflash the firmware, and then reset it. But basically, this gives us a backup option in case something happens with BMC. All right, so clock topologies. There's two potential ways that you can go here. As I mentioned earlier, we have the PCIe clocks coming across the cables. So if you want to implement a full common clock topology, you can definitely do that. There's kind of two ways you can fan out clocks from there. And this depends a little bit on the individual switch limitations and options that they offer. But either way, we have a local clock generator on the expansion board, which will certainly feed a clock to the switch itself. Then on the left side, you can see we can either forward the clocks from the generator directly to clock buffers on the drive plane board, which then fan it out to the SSDs. Or you have the option to basically drive the clocks on the drive plane board from the switch itself, if the switch has enough output clocks available. Both options are available, and again, the drive plane board is identical no matter which option you pick, because the fan-out buffers are on the drive plane board, and we have 4 inputs, so it's really up to you whatever option makes the most sense. All right, so I mentioned earlier different SSD form factors. So what we've designed so far is a couple of different carriers. So we've got a 2.5-inch 15mm SSD carrier, a 2.5-inch 7mm SSD carrier, because we have not yet aligned on a common thickness. But for now, we have options to support both. And then I mentioned earlier the M.2 option. So you see the carrier there on the right. That simply has an interposer board on it that fans out the PCIe, and I'll show that in a minute. And we can support both 22.110 and 22.80mm SSDs. All right, so this is the block diagram of the M.2 carrier. So basically there in green on the left is the connector itself. This just is the male version of the 8639 connector. So PCIe is basically directly fanned out. There's no additional logic in the path. It just connects 2 lanes to one slot and 2 lanes to the other slot. And as I mentioned earlier, the bifurcation is done within the switch itself just by modifying the configuration. The other thing we had to put on the board is 12 volts is provided through the connector. M.2 is run at 3.3, so we have a 3.3 volt converter there to step down the voltage for us. And then we have an SM bus MUX. We're going to support the SM bus sideband on M.2. So there's an ECN that was published a year and a half ago or so that provides SM bus connections on M.2s also, for the same reason that we want to use it on U.2s, right? So we want to be able to pull temperatures directly from the M.2s and feed that into our fan control algorithms. So this allows us to do that. All right, so from a power perspective, because this is another question I get a lot. So what are your power targets? You know, aren't the U.2 drives very power hungry? The short answer is yes and no. We chose basically to limit the slot power that we want to provide and cool to 14 watts. So by slot in this case, I mean the 3.5-inch bay, basically, or one connector. We chose that basically because from our perspective and the benchmarking that we've done, that is more than enough power to provide the performance that we're looking for. And you also have to keep in mind that the switches are oversubscribed, right? So there's no way that you can push the maximum bandwidth to each slot anyway. So there's no point in providing a power and thermal infrastructure to support the maximum power. So in terms of the power for the expansion boards, we've capped that basically at around 130 watts. We'd like to see that be much, much lower. I think that's perfectly achievable depending on the type of switch that you pick. But for now, we want to support up to 130 to give us a little bit of flexibility. And then total system power, which is the entire chassis, including fans, two SSD trays and so forth, is just under 770 watts up to. Finally, this is a quick preliminary snapshot of some thermal simulation data. In this case, the shot shows M.2s in the M.2 carrier. We have designed the M.2 carrier very carefully to ensure that we have optimal airflow over both sides of the M.2s. Obviously, one of the biggest challenges with M.2s is that the power density is quite high for such a small form factor. So cooling is very important. So we designed the carrier to basically funnel air very efficiently over the M.2s. And we are able to meet the component temperature specs even at 30% fan RPM. We still have some headroom. All right, so that was a lot in a short amount of time. So if you guys want to read more, the spec is already posted as Ashgar mentioned. If you want to see the systems, please come see us in the Facebook booth, the Wheelan booth, or the Intel booth. And then finally, I just want to say thank you to the extended Facebook team, the Intel and Wheelan teams, because there's a huge number of people that have been working very hard on this, and I really appreciate the help.
Great. So we have a few minutes if there's any question for Chris back there. Before I hand it over, Chris, the slides will be published on the MCP website.
Yes.
So you will guys have an access to those slides.
Chris, what divergent need drives the need for both a JBOD solution like Lightning and also the direct attach full height, half length card that you described earlier this morning?
Yeah, that's a very interesting question. So in general, our storage strategy at Facebook is to be very tiered, right? So we have 3 or 4 different storage tiers today, and we fully expect that may continue to grow a little bit further as the number of applications and data growth continues. So we definitely see value in having both options. It'll be nice to have a kind of local, high performance, higher endurance, very low latency flash solution that's local to a server, for example. And then we have this as an alternative that provides basically much higher capacity, lower throughput per terabyte, and in our case, potentially lower endurance as well. So this kind of gives us a much larger pooled approach versus a localized high performance approach. Does that make sense? Yes.
You mentioned about the retimer using one of the cards.
Can you wait for the mic?
So one of the cards that drives the cables actually uses a retimer, right?
That's correct.
Have you tried using a redriver?
We chose not to in this case because honestly the cost difference isn't very large, and the retimer pretty much guarantees performance, whereas the redriver only doesn't really clean up the incoming signal. So just whatever you provided, it's going to redrive, right? Retimer on the other hand will clean up the signal as it gets processed upstream.
That's true, but the retimer breaks the PCIe link training, right? Was that acceptable?
It does not break link training at all. The retimer we picked specifically has no issues with that. It will pass through all packets. Yeah, you're correct. There is an issue with certain devices that I'm not going to name that do have a problem with that, but this device does not. Yeah.
Next person.
I saw on the booth you have 2 kind of like switch solution. One is PLX, another one is PMC. So I think this slide will talk about PMC architecture. Can you talk about a little more about what you do with this PLX switch?
So the slides I'm presenting today are the architecture slides. They have nothing to do with a specific supplier solution. At this point, I cannot comment on specific supplier options.
Any other questions?
What is the purpose of the using M.2 because of the compromising the bandwidth from 5.4 to 5.2?
So I would say, first of all, I don't believe there is a compromise. Most of the devices that I see today are not even close to being able to push 2 gigabytes a second, which is really what is pretty close to what a by2 provides you as it is. So I don't think a by4 really adds that much additional value. And quite frankly, since you're limited by the number of lanes coming into the box anyway, you're not going to push more than that to the individual device as it is. So you're going to be upstream limited before you're going to be downstream limited, if that makes sense.
So you're thinking that
For the Facebook, the M.2 will be the major form factor instead of U.2?
It is one of the 2 options that we're evaluating. We're still in the process of deciding which makes the most sense for our applications. But the design supports both.
we still have time for 1 or more questions.
Do you have a plan to extend this to accommodate NVMe over Fabric technology?
So that's a good question. There's actually nothing in this design that precludes that at all. So if you want to run NVMe over Fabric, you can certainly do that from the compute node that it is connected to. I will also add that one of the advantages of keeping the switchboard modular and separate is that at some point in the future, if you wanted to embed something that translates Ethernet into PCIe on that board directly and just plug in Ethernet, there's nothing that prevents you from doing that.
Great. One more.
For power cell protection on SSDs, are wanting to keep that around, or is that something that eventually you'll be able to cost reduce out or use just standard client SSDs?
So for now, I believe there's still value in keeping it. The reality is that the added cost of power loss protection on relative to the media cost is relatively immaterial. But yes, in the future, it would certainly be interesting to build a design that creates a kind of common power loss protection, if that makes sense.
Thank you, Chris. Thank you very much.